Unless you've been living under a rock, you've probably heard of the video game Doom. And if you have been living under a rock, you've actually probably seen some computer scientists show up and try to get Doom running on your rock. And they probably succeeded. And you've probably heard the sentence, can it run Doom? So you've probably already figured out that in this video we are going to answer the question, can Redacted OS, the operating system that I've been working on since April, run Doom? But first off, why do people ask this question? What is Doom and why is it so famous for being ported and able to run anywhere? Well, first off, Doom was released in 1991. It looks like this. It was pretty much one of the precursors to the FPS genre and one of the first 3D video games to run on a personal computer. And because the game is so old and not particularly graphically intensive, it is pretty easy to port to modern machines. We'll talk about the specific reasons why Doom is easy to port in a little bit. But besides that, Doom is also now on GitHub. You can find the source that was released in 1997, download it, and try to get it to run on your own system. The code is also written in C, and as such, we expect it to be able to compile on modern compilers just fine. And finally, the code that was released is for the Linux version of Doom. Although there were other versions, this is specifically for the Linux version. And if you remember my last video, I talked about how Linux is POSIX compliant, and plenty of other systems are POSIX compliant. Because of that, a lot of the code is going to stay the same, and it's not going to need a whole lot of adaptation in order to get it to work properly on other machines that aren't Linux. You may also remember that I mentioned that my system is not POSIX compliant, and it's only a little bit Unix-like, but still, this makes our job a lot easier. So let's talk about the rendering a little bit more. Like I said, it is one of the very first 3D games to run on a computer. And this was actually a significant challenge, especially back in 1993 when the game was released. Well, computers were mostly thought of as business machines. And nobody was really asking for 3D spreadsheets, so they didn't necessarily have a whole lot of 3D rendering capabilities. Nowadays we have modern GPUs that are actually more than capable of running 3D games, but back then that was not the case. There was no hardware acceleration or even real hardware support for 3D. Everything had to be done by the software itself. Because of that, Doom and the Doom engine actually handle the rendering internally. That is one of the things that makes it particularly portable. So let's talk about porting Doom to Redacted OS. What did I have to do? This was my plan. First, we're going to get it to compile, then we're going to get it to load, and then we're going to get it to actually run the game. Easy. 3 steps, simple, we're just porting to an existing operating system, so this shouldn't take too long, right? Alright, it takes a little bit more than that. So let's start with step number 1, compilation. We're going to be using make in order to produce an executable file that Redacted OS will be able to read and execute, in addition to the ARM new toolchain that we use to compile both the operating system and any code that we try to run on it. As a matter of fact, I recently created a repository called the Redacted App Template that has a skeleton project for you to run your own apps in Redacted OS. Redacted now has some very basic third-party application support, and this template simplifies a lot of the setup needed in order to get apps to run on Redacted OS. I am planning to make a video maybe next week or the week after that where I talk more in depth about what it's like to make apps for Redacted OS, how to use this template, how to make apps, how to use the libraries that I provide. So stay tuned for that. I will go way more into detail into how to actually compile and make programs or even port programs, as is the case for Doom, to Redacted OS. But for the time being, what we need to know is that this template actually provides us with a makefile that uses all the project-specific compilation tools, the ARM new toolchain, although we need to download that ourselves. It then also links to the system's library, which provides syscalls and useful functions, provides a make run command that we can use to automatically compile Doom, put it into the system, and load and boot the system so we can test our program. And in case we need to debug, which we needed to do a lot of, we have a make dump, which disassembles the program and shows us the disassembly so we can see where something went wrong. And we'll talk more about it in the next video, but the debugging capabilities, especially for third-party programs like these, are very limited for the time being, so this tool is particularly helpful, although it's not the most comfortable to use. Alright, so just by using this and modifying the makefile in order to tell it to compile all the files that Doom needs in order to run, then we're going to run into compilation errors. This is kind of expected, but we have to fix them. they're relatively easy to fix. The compilation errors come from the fact that Doom was compiled for Linux, whereas Redacted OS, like I said, is Unix-like, same as Linux is, but is not POSIX compliant. And while a POSIX compliant system might be able to run it out of the box, I honestly couldn't tell you, but I think it could, well, Redacted can't. We have to make a few changes. Some things stay exactly the same. For example, both have a malloc call used to allocate memory. They work in the same way, and so we don't have to make any changes to it. Some other functions are slightly different in Redacted OS. For example, strlen, which is used to get the length of a string, works the same way that it does in Linux. However, it has a second argument, a max length, which allows you to truncate the string to a maximum length. Honestly, I might refactor this function and some others to make them a little bit more compliant with the C standard library, but this is the way that I built them because this is what I needed at the time that I built these functions. So for the time being, all we have to do is just add a 0 instead of max length to say that we don't have a maximum length. Then we have some other functions, such as sprintf. This function is being used by Doom in order to format a string and then print it into a buffer. Now, Redacted OS has a function to do that. It's called string format va buff, but it works in the same way that Doom expects sprintf to work, so all we have to do is replace the calls to sprintf with this one. We can even implement the sprintf function to call this one internally. Finally, there are some other functions such as fopen, which is used to open a file. There's also fread and fwrite. Now, Redacted OS actually provides a file system API to open and read files, not really to write files, but we can just ignore that part of Doom for now. So essentially, we won't have any save file support. But the thing is that the file system in Redacted OS is completely different from the file system in Linux or in POSIX compliant systems. So even though the function has the same name and works in a very similar way, we have to re-implement it to work with the structures and in the way that Redacted OS expects it to. So for the sake of simplicity, any function that has file systems or any other similar function that needs to be completely re-implemented, we are just gonna comment out the function or remove it entirely and add this not implemented macro and then do an early return, possibly with an error. The macro is simply just a printf with a bunch of characters to make it very, very evident and then saying that the function is not implemented. That way, when we run Doom and we start seeing a bunch of function not implemented prints, then we know we have to implement those functions because they're actively being called by the system. That way we'll also avoid working on functions that maybe are not actually needed because they're locked behind some functionality that we don't support. So after commenting out a lot of very important functions, such as the ones that render to the screen, the ones that get input, the ones that load files, pretty much anything that the game needs to do, well, we expect the game to run, but we expect to see one or more of these function not implemented prints, and then we expect the game to not run and show some kind of error. But actually, we immediately get a crash. And the crash comes even before any of these functions are called. So clearly something else is happening. Eventually, I traced it back to these two values, myargc and myargv. Now, argc and argv are arguments that the system can pass to a program when it executes it in order to customize the functionality of that program. And these myargc and argv are global variables inside of Doom that it is using to store those arguments. But whenever we try to access these variables, the process crashes. And if I look at the address where these variables are supposed to be stored, I kind of started to understand where the problem was. You see, these variables being uninitialized are put into a section of the elf file that we're using to load Doom called the BSS. And if we look at our linker file, it looks a little something like this. We expect the elf file to have a text section, which is the actual code, RO data, which is read-only data, data that we expect to read from but not write to, then a normal data section, which we expect to both read and write to, and that has an initial value. And finally, the BSS section, the one where these functions are supposed to be located, and that are supposed to be uninitialized. However, if we look at the actual elf file, the BSS section is not actually there. I believe this is probably some kind of linker optimization where it knows that the BSS section doesn't have any actual initial data associated with it. And so whenever the system is loading the elf file, it expects it to automatically allocate a certain amount of memory for the BSS section and initialize it. But my elf file loader is not the smartest. It actually just very blindly just loads the entire file into memory and executes it. I'm working on expanding it, but for the time being I haven't, and so it doesn't realize that there is a section missing because it has been optimized away. Now, the real solution to this problem would be to make the ELF file loader a little bit smarter. And like I said, I'm working on it. But since I wanted to implement Doom on livestream during a weekend, I kinda didn't want to waste time doing this. So instead, I just moved the BSS section earlier in the linker file so that it would be put in the ELF file without being optimized away. And that way, these variables were now accessible. Great, so now the program actually loads, but of course we expect to see a bunch of not implemented functions. The first and most important one that actually generates an error before anything else can happen is waddFile. Like I said, we commented out this function and added a not implemented macro and then did an early return with an error because this one uses the file system and we need to completely re-implement how it uses the file system. Now that part is not particularly difficult to do. I know how my file system API works, so I can just re-implement it. But the question is, what file is it trying to add? And the answer is a WAD file, or a WAD file, which apparently stands for Where's All the Data. These are data files that Doom uses. And these files contain all the map, level, texture, enemy data that we need. And so if we cannot load this file, well, there's not much of a point to starting the game because none of the data needed for the game is loaded. Now, like I said, it's relatively easy to implement the file system API in order to load this file, but where do we get this file? It is not actually included in the source, and as a matter of fact, it's not even going to be included in my source code version of this, which is available on GitHub, and you can find the link on the description below, because these are data files. You're not supposed to distribute them. Now, the shareware version, or the free version of Doom, can probably be found online. That's how I found it when I did the port, and it shouldn't be particularly difficult to find it if you want to try out the port yourself. But another thing you can do is just download Doom 1 and 2 from Steam and then use the WAD files that they provide. And that way you'll be supporting the small team of brilliant developers that put Doom together in the first place. Wait, oh right, it's published by Bethesda. Wait, who owns Bethesda again? Oh, fuck off. Alright, let's move on. Once we have a WAD file, there's another problem, the identify version function. See, this function tries to find any WAD files and sees, depending on which ones it finds, which version of the game is currently running. Because the game had multiple versions. There was Doom 1 and 2 could actually run off the same engine, but also the shareware version, which is just the first episode of the game and available for free. This is the one that I'm saying you can find floating around online. But also the commercial version, which is the one that you would get from Steam. Depending on which version of the game you have, it loads a different file, but it also restricts some features. The problem is, in order to identify the version, it needs to know which files are available. And as a matter of fact, yes, I do have a file system API, but I actually never provided a way to know if a file exists or not. I mean, technically you can just blindly try to open a file, and if you fail, you can assume that it probably doesn't exist. It's not the cleanest, I should probably implement this, but that's not the only problem. The identify version function actually uses a getEnv, or getting an environment variable called Doom WAD dir, or Doom Where's All the Data file directory. We don't have environmental variables, and we don't have a specific directory where this is found, so, of course, we can just hard-code the values of the WAD file that we expect. In my case, doom1.wad, the shareware version of the game. If instead you want to use the commercial version, you do doom.wad all capitalized or doom2.wad for Doom 2. So instead we can just hard-code these values for the time being. We're just going to make the identify version use the hard-coded doom1.wad and the shareware version of the game. If you're using a different file, you will need to change its name and possibly the version. So we move on and we find this error. Error init textures missing patch in texture door blue. Now at first, when I started debugging this issue, I thought maybe it's a bug in my system and I'm not correctly reading the file. Or maybe the actual file is missing. And doing some digging, I found out that this door blue texture is assigned a number once it is loaded by the engine. But it's not the texture that's missing, it's a patch. Apparently, the game patches textures. And the patch that it expects is mapped to number 256. And I even used a program called Slade at some point, which is a Doom map editor, which is also a WAD editor, and can be used to check out this WAD file and see if by any chance maybe the texture or the patches are missing. But from the looks of it, everything was correct, except patch 256 pointed to something called M1_1. This is not an actual patch. It doesn't actually exist. So what exactly is going on? By the time that this was happening, I had already been doing this for a few hours on stream. It was late, so I decided to call it quits for the day and try again the next day. And the next day, the best thing that can ever happen when you're programming happened to me. The holy grail of programming, guys. It exists. It's real. I've seen it. I googled the error, and someone with the exact same error posted the solution online. Turns out this blog from 2014 that also tried porting Doom to a 64-bit system ran into the same issue. And the problem was in this structure, which is used to load the textures. You see, Doom was originally compiled for 32-bit systems, and it didn't really account for 64-bit systems, because they were not popular, or maybe they didn't even exist, honestly I don't know, back in 1993 when this game came out. But Redacted OS is 64-bit only, and so I need to compile it for 64 bits. And the column directory property changes. It is a void pointer. Now, it being a pointer to a pointer doesn't really matter here. The point is that it's a pointer. And when you compile it for 32 bits, that pointer is 32 bits. But when you compile it for 64 bits, it is 64 bits. So it offsets everything after that, which is the patch count and the map of patches. So it's not that patch 256 was missing, is that 256 was the wrong number. It was part of the column directory pointer. And we can also see that the pointer is obsolete. It's not really used anymore. So we don't care too much about it. It is actually not referenced in the code. So instead of using its 64-bit version, we are going to replace it with a 32-bit int version. Like I said, this won't change the actual game because this variable is not used, but it will make the structure the correct size, and now we will be reading the correct number of patch, and we will find it. Again, incredible that I found the exact solution to the problem in this blog. And not only that, but actually by reading some of the other entries that this blog had, I was able to prevent and fix some other issues that happened later on, also because of this 32 to 64-bit transition. Honestly, I haven't seen any other 64-bit ports of Doom. Most people just resort to running it in 32-bit mode because most systems allow it, but Redacted OS is a new system, and so I never built it with 32-bit support. Even though the very first version of it was 32-bit, I moved on pretty quickly to 64 bits. So now the problem is fixed, and like I said, by looking at this blog, I was actually able to fix a few more issues before I encountered them. But still, the process crashes. And the process crashes with an address a little something like this, B4620. So it tried to access something at that address, and it failed, because there's nothing at that address. Now, you may think the issue may again be something with the size of pointers or something like that, but I already know that that address is a little bit weird. You see, Redacted OS loads itself at this address right here, 410.000.000, and everything is loaded after that address. So if we try to access address B4620, that is way lower than it should be. There's something else going on here. Well, I trace back the issue to this function, initSpriteDefs, which takes this argument, a char pointer namelist, or colloquially, an array of strings. Specifically, when it tried to access the first value of namelist, it tries to access it at address B4620. That address is completely wrong. That's not where the program is loaded. It is loaded beyond that 41 address, actually more likely to be 42 or 43. Depending on what else is loaded in the system. So what's going on? Well, you may remember when I talked about ELF files that most of the times that they use addresses, they use relative addressing. So for example, they try to branch 10 instructions back or load a value 30 instructions forward. Because of that, the ELF file is pretty position independent by itself. It doesn't matter where the code is actually loaded, it will still be able to find the correct functions and the correct values, variables, and functions at the expected place. However, when we try to access a char pointer, then it actually tries to load the absolute address of that string, which should be 430B4620. But instead, it loads just the B4620 part, because that is its address inside the ELF file. that should be its virtual address. I talked about virtual addressing when I talked about the MMU, but I also mentioned that I don't support virtual addressing. So now we can kind of understand what's happening. The code expects to be loaded at a virtual address, which we are not doing. And we're also not compiling with the position-independent executable flag, which should prevent this issue, but actually requires the elf file loader to do a little bit of extra setup. And like I said, my loader just copies the code and executes it. So while I'm still working on supporting these kinds of features, I currently don't, and so that wouldn't work either. So what did I do instead? Alright, let's begin with the disclaimer. It is a hack. Do not do what I did. I really thought this was only gonna happen a couple times, so I came up with a quick and dirty hack that could just solve the issue for the time being, and then once I created a proper elf file loader or proper virtual addressing support, which I was planning on doing soon anyway, then I could do it properly. But as is often the case with hacks, this hack ended up being way more cumbersome and way more time consuming than if I had just implemented those features directly. So don't do what I did. Alright, so the hack essentially consists in the fact that the code expects to find our variable at address B4620, whereas the code is actually loaded with a base address of 434.00000. So inside my init sprite_devs function, I just add the base address, or the 434 part, to the address that it expects, the B4620, thus creating the absolute address. See why I say you shouldn't do this? It is ridiculous. And yet, it worked for a bit, until it didn't. Eventually, I ended up having to implement this hack in so many places and actually having so many issues with it that I gave up and decided to implement a very basic rudimentary version of virtual addressing. And guess what? It took me like 10 minutes and 3 lines of code. These. Actually, if you don't count the brackets, it's 2 lines of code. It was super easy to do. Now, like I said, it is a rudimentary version of virtual addressing. It means that only one program can be loaded into a virtual address at a time, and there are heavy limitations into what those addresses can be, but hey, it kind of works, so. It's definitely better than having to add a base address every single time, which, by the way, also required me to load the program in the same place every single time. You see why I say it's ridiculous? 2 lines of code, or 3 if you want to be pedantic with the brackets, is all that was needed to prevent this hack. So great, now we have Doom running. Wait, oh right, we haven't implemented any graphics features or anything like that. Alright, so in order to implement graphics, and for the matter input, all of that is found in the ivideo.c file. In here, we will have to re-implement completely all the graphics functions and the input functions that were specific to Linux and actually to X11. Luckily, it's not that many functions. Here's the first one, init graphics. Here's where you created the X11 context and the window and whatnot. I honestly don't know how X11 works. I've never worked with it. But here's how it works for Redacted OS. You have to request something called a draw context, which is essentially the frame buffer in which your window will be drawn. Now, actually, windows are not provided by the program itself. In Redacted OS, things work a little bit differently. I will talk more in depth about it in future videos, but essentially, the user creates a window first and actually draws it to decide its size, and then the program is given that window. So you don't create the window, you instead request the draw context for the window that already exists before your program is even initialized. So all we have to do is request it and put the data inside a draw context pointer. Draw context is provided by the systems library. Then we have the start frame function. This doesn't actually include any rendering code, it includes input code. And likewise, we have to replace the X11 input code with the Redacted OS one. In Redacted OS, you can call a read key function and pass in a key press structure in order to receive input if any is available. And if it is, we pass it into an event T structure which Doom provides, and then call the dPostEvent function, which makes Doom aware of this event. Now, the code that I'm showing here is quite simplistic. It is just for illustrative purposes. It's really a little bit more complex than that, so it can handle multiple keys at once. It handles key down and key up events. And there should also be mouse support, even though I haven't added that yet. But this is how it works. We also use this xlate key function, which used to translate keys from the X11 key codes to the Doom key codes. Now we just replace the X11 key codes with Redacted OS's key codes. It's simple, but the problem is that The macros used to define the key codes, both Doom and Redacted OS use a lot of the same macro names, and so they kind of conflict with each other. So I replaced the Doom ones and just called them key Doom something. But either way, this function is relatively simple to implement. And finally, we have the finish update function. This is where actually drawing to the screen takes place. Now, Doom has its own renderer, like I mentioned, and actually it is a work of art. I won't explain how it works here because there's already plenty of people that have done it and understand it way better than I do, because I have only a very basic understanding of how it works from watching their videos explaining it actually. But this simply means that we just have to translate the data that Doom gives us and put it into our frame buffer from the context that we requested in the init graphics function. And actually, you will see that we're using a colors variable here. This is one that I'm going to create in the next function. Then you will see that I'm setting a full redraw flag, which is used to tell Redacted OS that the entire window needs to be redrawn, because it also has the option to redraw only specific parts of the window. And finally, we call the commit draw context, which sends all the frame buffer information to the system in order to be rendered into the window. Besides that, we have to re-implement or tweak a little bit of the functions that Doom already provides, such as set palette. This is the colors array that I talked about before. You see, Redacted OS uses 32-bit colors. Doom uses an 8-bit color palette. Not the colors directly, but a color palette. So it's limited only to 256 colors, but actually, depending on the palette, it determines which colors. And from my very basic understanding of how games worked back then, which honestly is not a whole lot, essentially, you could have more than 256 colors by simply having different palettes and switching between them when switching levels. So maybe a specific level could only have 256 colors, but the entire game could have more than that by using palettes. Not only that, but I believe you can actually get quite clever with your usage of palettes. For example, let's say that you have a black screen. So all the values in the frame buffer are currently 0. If we don't use a palette, then this is simply black. And then let's say that we want to draw to only part of the screen, because the rest of the screen is currently not being rendered. There's no data to render on there. But if we, instead of simply mapping 0 to black, if we cleverly use color palettes, we could make it so that 0, for example, is blue. And that way, we're clearing the screen with a specific color just by setting everything to 0. Besides that, we also have to implement the read screen function. Honestly, this function is not particularly complicated. I'm not sure why I commented it out in the first place, because there's nothing in here that I needed to replace. The code that was there was fine, but for whatever reason I disabled it, and that was preventing certain things such as a screen wipe animation and the HUD from drawing correctly. So finally, after all that work, we have Doom. Okay, we have the main menu of Doom, but it's a start. And actually, at this point, I still had to deal with a lot of those absolute addresses that I mentioned, but I already mentioned it once, so I'm not going to talk about it. It held me back quite a bit until I finally decided to implement virtual addressing. But once that was the case, and I fixed another crash for which the solution I found on that blog that I mentioned earlier, I was finally able to enter the levels. And for that matter, there should be a demo that plays in this point. But instead, Doom showed an error, saying that the version of the demo in the WAD file and the engine were different, so it wouldn't play the demo. But this is easily fixed by just changing the version for the game engine to the same one in the WAD file, in my case 109. And just like that, we can even get a demo playing behind the main screen. So as you can see in the demo, the walls look a little bit weird, but eventually someone that had been following along the process figured out what the problem was. Remember this? I mentioned how that void pointer was giving us issues because of the way that it grew from 32 to 64 bits. Well, that's fixed, and all the other values should work the same, but look a little bit closer. That Boolean value. Booleans are not a normal type in C. Normally, whoever creates a program implements Booleans for their own convenience, but they're not standard to C. And the thing is that this is how Doom implemented them, as an enum with a true or false value, whereas I had implemented them with my own bool type, which was actually an 8-bit value, whereas the enum is actually an int, or a 32-bit value. So actually now the boolean was too small, and so some textures didn't load correctly. So with that fixed, finally we have walls. But as you can see, there is still a rendering bug. It looks a little weird, and to be honest, this is a bug that I still haven't been able to fix yet. I don't think it has anything to do with 32-bit values or with the way that I have implemented things on my end in my system. And actually, I found this code where it seems like the programmers of Doom were actually referencing this bug and trying to fix it, but it doesn't seem like they were able to, so I think this will require a little bit more debugging. I don't know exactly what happened in my port specifically that made this code more buggy and made this bug appear more frequently, but I have found some threads online where they discussed a similar bug, so I don't believe it's necessarily from my port, or at the very least not exclusively. With that being said, I believe that while there's still a few things to fix, mostly the rendering bug, as well as also maybe adding mouse support, sound support, and maybe even network support, although that one's a little bit far-fetched, code for my Doom port can be found on GitHub. I do believe it is, alongside the one I found on the blog that I mentioned, which is also linked in the description, one of the very few 64-bit ports of Doom. Finally, I would also like to thank YouTube user GStudios for helping me throughout the porting process to find a few bugs, such as helping me figure out why certain things such as screen wipe were not working, as well as fixing the wall texture bug. And also taking a look at the rendering bug, although we haven't found a solution for that one yet. And I think we can officially answer the question, can Redacted OS run Doom, and say